Hello, thank you very much for the opportunity to present to you today. My name is Michael Dorin, and I teach software engineering for the University of St. Thomas in St. Paul, Minnesota. I am also working to finish my doctorate with Dr. Sergio Montenegro of the University of Würzburg in Würzburg, Germany. I truly wish I could be in Columbia today, but perhaps a future conference. I have been working with Dr. Montenegro on establishing a means or a method of classifying how complicated software source code is. Not from the perspective of how complicated it is to use software, but rather from the perspective if somebody has to go and look at source code produced by a programmer, perhaps for maintenance, how complicated is that source code to read, understand, make changes and adjustments to? This has truly been an interesting project. As this is a linguistics conference, it's very likely many of you are already familiar with George Ziff. And many of you are probably already familiar with his principle of least effort. As I'm applying this work in a new manner, and for the software engineers in the audience, a quick introduction is probably a good idea, and perhaps it'll give you some insight as to my point of view on this matter. So as a reminder, who George Ziff is, George Ziff was an American linguist. Among other things, he studied the statistical occurrences of languages. His work spanned the 1930s through the 1940s, and he died in the early 1950s. Obviously, Professor Ziff is not the only one who studied these concepts, the statistical occurrences and whatnot, but his principle of least effort is what we will focus on here. So to give you an idea of what is the principle of least effort in a nutshell, or a summary version, Professor Ziff hypothesized that humans, in all of our endeavors, not just language, will select actions to perform based on the most efficient way to complete a task. If you review a copy of his book on least effort, you'll see that he doesn't just stop with linguistics and language. He covers a variety of topics, actually a great deal of topics. By the way, one more thing to keep in mind. When you think of the principle of least effort, don't think about it in the perspective of laziness. Think about it as a desire for doing things in an efficient manner. So continuing to illustrate the principle of least effort, Ziff illustrated the principle by describing artisans who must survive by performing work with a set of tools in the most economical manner possible. For the artists to use their tools with the maximum economy, with the maximum efficiency, they must arrange them in such that the sum of their usage efforts will be minimum. They'll basically get the most profit out of their usage. We suggest that this also applies to the creation of software works as well as the maintenance of software. So this principle isn't just applied to linguistics. So there's already other areas where it's used. One example is in the field of library science. So researchers in the field of library and information science suggest that information seekers will tend to use the most convenient search method available. And they'll use this most convenient search method available in the least exacting mode available, so the least taxing mode. And they'll do these searches, they'll seek their information only until they find enough to accomplish what they're looking for, not an excess abundance of information for a better product. As teachers and professors, I think we could probably think of examples of that, real life examples from the work our students have produced. If you're interested in more details, the link on the screen can give you a larger background on this assertion. Oops. All right, so does everybody agree with Ziff and agree with the ideas? Not completely. In the introduction to the reprint of Ziff's Psychobiology of Language, George Miller suggested that a collection of monkeys with typewriters could get the same size and frequency distribution as Zipf's law of vocabulary balance, which is related to the principle of least effort. George Miller did suggest that Zipf was correct on many things, but if I read George Miller correctly, George also suggested that Zipf perhaps didn't understand why he was correct or what he was actually discovering. But think about it. So, is this principle moot because randomness could produce the same results? So, I'm not a monkey behavioral expert, but I wanted to get a little bit more understanding of what might happen. There's many ways to think about how monkeys might type, but I think the suggestion was that monkeys are going to type in a random way, and eventually, remember the old adage that enough monkeys typing will eventually type Shakespeare. So the simplest idea, and probably the most prevalent idea, is to think of monkeys typing purely randomly. So I wrote a little application to simulate monkeys typing random words. Interestingly enough, the distribution of the size of the words does come out to be logarithmic, but the distribution of individual words, at least with my 10 million count, when I let the monkeys type until 10 million words, the distribution of individual words themselves did not happen to come out logarithmically. And the fact of the matter is that without a fixed set of words, it's sort of hard to believe that it might come out logarithmically. The sizes, yes, but not the individual words. Of course, you might be thinking, what does this prove? And it doesn't really prove that Zipf was correct or incorrect. The one thing that I think I'd point out is that it's probably not completely fair to compare Zipf's work to a random act. If we really wanted to compare it to monkeys typing, we would have to start thinking about what goal might a monkey have, because a monkey would have a goal. If the monkey was typing, the monkey would have a goal. Perhaps the goal was to get fed more, or whatever. The monkeys would have a goal. And I believe likely the monkeys would evolve to using the least amount of effort to achieve their goal. So not saying that more study is warranted, but if there was going to be more study, we would actually probably have to even understand what their goal is. So how does this apply to software? As it turns out, as you might suspect, software writing is a human endeavor. I've heard software development compared to authoring a book. I've heard software effort even being compared to creating a sculpture. If we look at something else that's not software related, think about playing a piano. And it's said that playing a piano is connected to mathematical ability. So I sort of think of software composition the same way as musical composition, in a way, that there is a connection to mathematical ability, but writing software is still very human and very artistic. And I don't think that we can take the artistic and the human portion out of the equation. Now, the desire for understanding how complicated software is goes back a long time. The very famous traditional software metrics were from McCabe and Halstead, but there's dozens or perhaps even hundreds more. One metric that's even simpler is the lines of code. The number of lines of code in a file equates to how complicated the file is. And by default, the more lines of code, the more opportunity for complicatedness. McCabe just opposed. McCabe suggested that the number of decisions contributed to how complicated software is. And Halstead counted operations and operators. And that's not to say that these pioneers didn't come up with anything useful. I personally believe that their work was very useful, but I don't believe that their work necessarily represents the behavioral science side of how complicated software is. So considering software is as much as anything an artistic endeavor, I think that it's not complete to evaluate it like perhaps a mechanical proof. So back to the artisan. So what are the tools of the software artisan? So besides the obvious, we think about compilers, operating systems, utilities, servers, etc. Ones and zeros. When we're writing the software, we have the components of language and components of expression. So summarizing, and maybe linguists out there will tell me that I'm missing something, but when we think about language, we think about syntax and we think about semantics. So for syntax is, for us, syntax, I'm going to consider statements and expressions make up the syntax. In semantics, I'm going to suggest that identifiers are human chosen, so identifiers relate more closely to semantics. Obviously, in software, we cannot ignore the logic as well, and we're going to address that as we go along in our research. But logic was nicely reviewed, nicely measured using traditional techniques. So this paper, we're going to focus on syntax and semantics, and specifically statements and expressions. The other topics, identifiers and algorithms, are going to be addressed in future work or have been addressed by other authors. So how do we start? So what Ziff did when he started was created a corpus and a rank frequency calculation of the novel Ulysses. And in the novel Ulysses, Ziff tracked the words, basically how often the words were used, and compared them against the rank of the words. So the most used words had a rank of 1 or smaller, and the least used words had the higher rank, sort of like coming in first place, second place, etc. So we did the same thing with statements and expressions. So we downloaded a large collection of files from GitHub, open source projects from GitHub, with millions of lines of code. We separated the statements and the expressions. We built a corpus, and we did a count of basically the frequency of use of each of the statements, expressions that were found in the projects that we downloaded. When we plotted the frequency versus rank table like Ziff did with the novel Ulysses, we got a picture very similar to what Ziff arrived at with the novel Ulysses, with a slope of very close to -1, just as Ziff had remarked. So basically, we're suggesting that the most used, the values of the higher frequency, we're going to call that the Ziff score. The higher frequency are easier to comprehend because they're used more often than the values with the lower frequency, a lower Ziff score. So how does this map to software sentiment? How does it? Basically, the easier statements and expressions are going to be used more often. They're going to be used as frequently as can be efficiently done more often than the most used. And we can see some examples. So on the lower right-hand corner of the screen, we see that the else statement, for example, that was the #1 used statement in the collection. Now at the top of the screen, in the top right-hand corner, we see an example of an expression that was one of the least used ones. And you can notice, how much different, how much more complicated that one is to look at than the ones in the lower right-hand corner. Mind you, I've substituted the real name of the ID for ID and the real string literal for string literals, but you can envision how complicated this statement might be. Now, if you're wondering, why are there so many else's? Why wouldn't there be an equal amount of ifs? Now, we have to remember that if is a logical statement, and if requires an expression, that's a statement expression to do the comparison. So there's a lot of different ifs, but you can see that as the ifs get a bit more complicated, that their frequency of use seems to tail off. So this is only a small number of the ifs that we found in the corpus. So there'll be a lot more else's than ifs. All right, so back to how do we see if Zipf's ideas have merit? We consider two paths. 3 years ago, we asked programmers to review source file and indicate from a purely aesthetic point of view if the file was pleasant or unpleasant to review. No more than that. We identified the files that were leaning pleasant to review and unpleasant to review, and we extracted the statements and expressions from those files for further analysis. On the second path was to count and compare the number of faults in the files. And we used tools created by Milton Fedelstein of the Hebrew University in Jerusalem for counting faults in a project. And finally, remember the concept of negativity bias. So if we could think about how one apple can spoil a bunch of apples, negativity balance relates the same way. Basically, a few bad statements can make an entire file undesirable. So from a human point of view, we won't assume a source file that has some ugly statements is great, even if it has a lot of nice statements. All right, so what are the results? We believe the results show merit. Remember, the Zipf frequency score refers to the frequency of use of a particular statement. Statements with a low frequency of use, we suggest, are harder for people to understand. We had more unpleasant review. In our study, we had more unpleasant review files, leading to a little bit of an unbalance. But notice in this histogram, the trend line from the pleasant to unpleasant in the histogram maps nearly perfectly, unpleasant being the red and the blue being pleasant, except at the very low Zipf frequency of use. So basically, the unpleasant review files, and think negativity bias, had more rarely used statements and expressions than the pleasant review files. And since they're rarely used, we surmise they're more complicated. Counting bugs is a bit trickier. Bugs can only be spotted if they are found, reported, and fixed. Sort of like a tree making a noise if it falls in the forest and nobody is there. For this project, we considered something to be buggy if it had more than 50 bugs per 1,000 lines of code, and not buggy if it had 15 or less 1,000 lines of code. In Table 4, shows there seems to be a small relation on larger projects of bugs to Zipf score. So projects that have more than 50,000 lines of code, buggy projects that have Zipf score of about 3.7, non-buggy about 4. But for small projects, the Zipf score didn't seem to make a big difference. We also took a peek to see if, based on the number of bugs per kloc, how the Zipf score worked. And there seems to be a trend in that. But admittedly, we had very few hugely buggy projects to compare to. So perhaps another peek at that later on. But it does seem to be a trend that as the number of bugs per kloc grows, the Zipf frequency score seems to decline. So it does seem to be that there is a relationship between bugs and the frequency score. So like I said, mapping to bugs is a difficult task. So what's the takeaway? Since software source code is difficult to measure with traditional metrics, this could be a new era of applied linguistics, studying the source code, the implementations. I'm not the first to think of using Zipf with software. These studies show that application of Zipf's work to software can yield positive research outcomes. Thank you again for listening to my presentation. I believe that following the path to natural language can lead to an exciting new era of measuring software code written in computer languages. So I believe that this is a new way of looking at software source code and evaluating source code. We will be continuing our study with identifier analysis as well as how this couples to logic. Once again, thank you for attending and watching. And I appreciate your attention today. Thank you. Bye-bye.